Section 4.2, we're going to be looking at experiments, how to conduct them well, what are some important things and principles of experimental design. Okay, so first thing is we have to understand the difference between an observational study and an experiment. Okay, so in an observational study, we are just observing. That's why it's called that. We are just watching and recording results. But in an experiment, we are deliberately using a treatment. Okay, so think like middle school science fair. All right, so in an experiment, I'm intentionally changing something about the environment, but in an observational study, I am just watching what happens. So here's an example of why this is important. I want you to take a second and read through this information about hormone replacement. Okay, so in the 90s, they had some observational studies, basically where they were just following women who chose to have hormone replacement therapy versus those who did not, and they found that there was much lower risk of heart attack. However, because this was not an experiment and they were just observing what was happening in nature, they did not take into account the fact that most of the women who were taking hormones were richer, they were better educated, they saw the doctor more often. And so what they had to do was do an experiment where they randomly assigned women to different treatments so that they could see whether the difference was the hormone therapy or the education level and the amount of money that someone had and how often they saw the doctor. All right, so the reason that observational studies can't necessarily be used to prove things or imply causation is because of lurking variables. So that's something that was not part of the study. They didn't intend it to be part of the study, but it can influence the result. So for example, in our hormone replacement therapy, the amount of time that women saw doctors, okay, it is difficult to say whether it was the hormones or the doctor's visits. Confounding is what the lurking variable causes. Okay, so if there is a lurking variable present, it can cause confounding. It can cause us to not be able to tell the difference between the variable that we're trying to study and the one that we did not control for. Okay, language of experiments, vocabulary here. Some of this you're probably going to be very familiar with from previous science classes or if you took AP Psych. Okay, so in an experiment, we have a treatment. The treatment is the thing that we are applying. So hormone therapy or not, those are treatments. Okay, we apply the treatment to experimental units. You might know them better as subjects. So the subjects of the experiment are the experimental units, the people, animals, or things that we are experimenting on. And then the response variable is what we are measuring. So in that previous study, they were measuring how often people had heart attacks. Okay. Little note here at the bottom, sometimes you'll see the word factors used. A lot of times this happens when we are studying more than one variable at a time. We have different factors, and so we can combine them in different ways, and we'll talk about some examples of that. So here's our example. We are comparing two medicines to treat head lice. And so we have a study of 812 people in 376 households. We have 185 of them randomly assigned to ivermectin and 191 of them randomly assigned to malathion. No idea how to say that. Okay, and so we need to identify the following. What are the experimental units? What's the explanatory variable or variables, response variables, and treatments? I want you to pause here and see if you can figure this out, and then we'll go over it. So our units are going to be the households, right? Even though we said we had 812 people, we decided who gets what medicine by household. All right, so those are experimental units. The explanatory variable, the thing that we are testing, is the type of medication, the two different kinds, and then the response variable that we are measuring to see if the medication works is whether the household was lice-free. Okay, and then our two treatments are the two different medicines. All right, so something that we can do to try and fix confounding, all right, is, as in all things statistics, introduce randomness. So we want to assign treatments to our subjects randomly, okay? And the goal is to create 2 groups or 3 groups, however many treatments we have, that are similar. All right, and so if the groups are similar to each other, then I can determine whether or not my treatment is the deciding factor. So the first thing is a completely randomized design, all right, where I take my units, my subjects, and I just randomly split them, completely random, similar to like a simple random sample. I am just, a lot of times we'll do this by drawing things out of a hat. So I will, if I have 50 units that I want to split between 2 groups, I'll draw 25 numbers out of a hat. Those people go to group 1, the other people go to group 2, and then that's how we decide what treatment they get. All right, so here we have an example. A health organization wants to know whether a low-carb diet or a low-fat diet is more effective. And then they're going to also have a control group that just gets a brochure, and they don't tell them anything about what diet they need to eat. So we have 90 volunteers who are going to participate in this study for 1 year. Okay, so if I want to do a completely random design here, my design is going to look something like this. I have my 90 volunteers, right? And then by a process of random assignment, I am going to assign 30 of them to a low-carb diet, 30 of them to a low-fat diet, and 30 are just going to get a brochure. And then at the end, all 3 of those, I am going to compare. And if we're doing weight loss, we're probably going to compare their weight loss. Okay, we're going to see how many pounds each of them lost from the 3 different groups. Okay, in an AP exam situation where you are asked to design an experiment, this diagram you can definitely draw, and it's a good starting point, but you also need to include a sentence or 2 about what this diagram means and how you're going to do your random assignment. So your answer might look something like this, where you draw the diagram and then write and explain how the diagram works. Okay, 3 principles of experimental design that we need to always take into account. One is control. Okay, have we tried to identify any lurking variables and done something to control for those so that they don't affect our results? All right, random assignment. Okay, we should not be picking and choosing what subjects get what treatment. Those should be assigned randomly. And then replication. Have we used enough people that we have accounted for any outliers? So if I have a really small group of volunteers, like 5, then an outlier could throw that off. But if I conduct my experiment with 200 people, that kind of smooths out the effect of any outliers. Okay, so what are some things that could go wrong that we need to account for? First is the placebo effect. So sometimes just giving people a pill or something will make them feel better, even if it doesn't have any physical effect. So that's why a lot of times you see placebos given in experiments. So that they can see whether it's the actual medicine or just the fact that you're telling someone you're giving something that's going to make them feel better. All right. We also like to, as much as possible, have what we call double-blind experiments, meaning neither the subject nor the experimenters, the people who will interact with them to measure their results, know what treatment they're getting. So if I'm comparing like aspirin to a placebo, We want the pills to look exactly the same so that people don't actually know what they're taking. And then the researchers that are going to be talking to them and measuring results, they don't know whether that person is receiving real aspirin or a placebo. All right. And so what we are looking for is we want to see a large enough difference that there's no way it could just happen by chance. And that is what we call statistically significant. All right. So later in the year, we'll learn about what actually makes something statistically significant and what numbers we're looking at. But basically, we're looking for a really large difference. Okay. Now, sometimes we have confounding variables that we need to take into account. And an easy way to confounding effect is to use what's called blocks. And so before we do the random part, we intentionally separate people by some characteristic. It could be gender, it could be age, it could be experience, it could be weight, it could be anything that we think might affect our experiment. So we intentionally separate people into blocks, and then within each block, we randomly assign people to treatments. Okay, so if we look at our weight loss experiment from before, men and women often experience weight loss differently. Okay, so that could be a potential source of confounding. Because in our completely random design, there's a chance that one diet could have more males than females just by chance, and that might affect our results. So when we block, we would split our volunteers into males and females, and then within each group, they randomly get assigned to one of the 3 diets. Okay, so if I change it to look, it would look something like this. So now I'm comparing men to men and women to women, and so that would eliminate gender as an issue of confounding. All right. Important thing to know, blocks are intentional. So these right here, the male, female, these are my blocks. The blocking part is intentional. Blocks are not random, but within each block, they are randomly assigned treatments. Okay, so blocks are intentional to eliminate a lurking variable, but then within each block, treatments are randomly assigned. One more type of design that we can look at is called matched pairs. And in this case, we are directly comparing 2 people or 2 subjects to each other. Okay, so, and then within that group that we create, we randomly assign who gets what treatment. The most common example you'll see of this is identical twins. So if I have a set of identical twins and I randomly give one twin treatment A and the other twin treatment B, that allows for a really good comparison because identical twins have the same genes and all of that stuff, so it allows me to compare. The other thing that you might see with matched pairs is one experimental unit gets both treatment, and we randomly decide the order. Okay, so we'll look at an example of that. We have some cardiologists want to test whether chocolate affects blood flow. And so they have some volunteers that they're going to give either actual bittersweet chocolate or fake chocolate. All right, and so they are randomly assigned to which one they get, and they eat the chocolate, and then they come in and they get an ultrasound of their arm. Then on another day later, all right, they come back and they eat the opposite. So if they got chocolate before, they get fake. If they got fake before, they get real. And they do the ultrasound again, and then we compare each person only to themselves. Okay? And the reason we do this is we have to have 2 people might have different blood vessels to begin with, so we want to compare them to themselves. And the reason that we decide the order of chocolate or fake randomly, if we gave everybody chocolate on the first day and everybody fake on the second day, we don't know if the day is causing the difference or the chocolate. Okay, so that's a second example of matched pairs where you're comparing people to themselves. And that's all we got for 4.2.